So we're going to talk about serine proteases first in terms of mechanism because, well, we know a lot about them. We know how the mechanism works, and it also illustrates several of the principles we just talked about. So trypsin and chymotrypsin, these are major proteases. Well, you learn about them as tools, but of course they're also secreted from your pancreas into your intestine, and they help in digestion of proteins in the diet. Elastase is another enzyme. They all look very similar in terms of their protein fold, which I'll show you in a minute. Cetylysin is another serine protease, looks nothing like them, quite different. However, every serine protease has a catalytic triad, that is 3 amino acids that work together: an aspartate, a histidine, and a serine. The aspartate, so basically the serine is the reason why we call them serine proteases. This is what makes a nucleophilic attack on the carbonyl carbon of the peptide bond that's going to be hydrolyzed. The histidine serves as a base to abstract the proton from serine, and later on also as a proton donor to the leaving groups, as you'll see later. The aspartate makes histidine a better base by making a low barrier hydrogen bond to the other nitrogen of histidine. If you look at the primary structure of trypsin, first of all, it's cut twice, here and here. There are actually 3 chains. It is initially made as a long precursor called chymotrypsinogen. The ogen at the end lets you know that it's a precursor. And then it's clipped, actually by, if I remember right, trypsin and other proteases, and maybe even by itself, to generate the mature enzyme, where a few amino acids are missing, 14 and 15, and 147 and 148 over here. Now, if you look in the primary sequence, histidine 57, aspartate 102, serine 195, these are the catalytic triad members. They are nowhere near each other in the primary structure, but in the tertiary structure, they will be. As is often the case in secreted proteins, there are several disulfide bonds as well, but which we're not going to really pay attention to. Here's a catalytic triad here, the aspartate, histidine, and serine. These residues over here are what we call the oxyanion hole that stabilizes the transition state. Here's a different view of that, the aspartate, the histidine, the serine. It's kind of in a cleft of the enzyme that the substrate will bind. Here's a substrate going in. This is chymotrypsin, so there's a pocket for the aromatic group. This is looks like a phenylalanine, or maybe, no? I think it's a phenylalanine. There's the alpha carbon. Here's the carbonyl carbon. The oxygen, which is purple for some reason, is over here. The nitrogen of the peptide bond that's being hydrolyzed right there. And that places this carbonyl carbon right next to the serine, which is going to do the nucleophilic attack. And it's next door to the histidine. The aspartate would be over here. You can't see it. Okay, so this just reminds you of our players, aspartate, histidine, serine. Let's start the mechanism. So we've got this nice cleft to bind the polypeptide chain. We position it by the aromatic group going into the hydrophobic pocket. And that will place what we call the scissile bond, the bond that's going to break right next to the serine, the carbonyl carbon right next to the serine oxygen, and the oxygen right next to 2 amine nitrogens pointing right at it. So they're donating. So there's some partial positive charge from this dipolar bond. Okay, and the nitrogen of the deprotonated histidine is accepting a hydrogen bond from the serine. Now, what's going to happen in this mechanism? And they didn't actually draw it completely here in the book, so I'm going to finish it for them. What they didn't show is this nitrogen, whose lone pair is coming out here, again, a hydrogen bond, is going to take that hydrogen from the serine, okay? Allowing this oxygen to be a much better nucleophile, so it can attack the carbonyl carbon. And the electrons, the double carbon-oxygen double bond, one of the bonds is going to go into a lone pair of the oxygen, making an oxyionic state. All right, so you might ask, why is histidine, which has a pK of 6, deprotonating serine, which is a pK of 13 to 14? Doesn't seem very likely. Well, the low barrier hydrogen bond over here, which is just barely shown from that aspartate, 102, is actually causing the pK of the histidine to effectively be much higher. Because if you have a low barrier hydrogen bond, that means this hydrogen is partially shared with the aspartate, which means this histidine actually doesn't have a complete proton there. Now, the pKa of imidazolate, okay, so if we had this, where both nitrogens are deprotonated, then the pKa of just free imidazolate, so if I were to take away this, just that molecule there, that pKa is 14. The pK of imidazole, just free imidazole, is about 7. 6.95, we'll call it 7. Okay, and in histidine it's about 6. So you can see the huge pKa shift by deprotonating the imidazole. Okay, so the imidazolate is a very strong base. And so by taking part of the proton away, you're shifting it more toward an imidazolate, okay, which makes this a much better proton acceptor. So essentially, the proton moves over here, this oxygen attacks here. And actually, now, essentially, you'll have formed a new hydrogen bond between the histidine and the serine, except now the histidine is the hydrogen bond donor, as you can see. Well, actually, it's moved over here now. So it'll initially be a hydrogen bonded over here, then the histidine moves slightly over here, and it's actually it's a very tiny move, okay? Now it's donating a hydrogen bond to the lone pair of the nitrogen. And that will allow is now when the electrons push up from this oxygen, and by the way, now we have the oxyanic state. Now you can see why this is called the oxyanion hole. It's a little cleft in here where the oxygen binds in, and you stabilize this state. Now this state is not technically speaking a transition state, because you can actually technically observe this. It's short-lived, but it's not infinitesimally lived. Probably on the way to getting to this is a transition state. But it's an intermediate state, and this oxyanion hole stabilizes that. Okay, but it's not very stable, so these electrons are going to push back, and you're either going to break this bond that you just made, or you're going to break this bond, which is what you want to do. And by the histidine being over here to donate a proton to the nitrogen, that will then produce an amine here, where one of the protons was there already, and the other proton came from the histidine, which came from the serine originally. Okay, so it's moved the protons moved from the serine to the histidine, and now to the new amine, which will leave. So the C-terminal part of the C-terminal peptide will leave. Okay, remember the cleavage is after phenylalanine. The peptide of the substrate is actually running from right to left. Usually, not the way we usually look at it. Okay, now, so that's left, and now we have this state where the amino terminal peptide, which ends in the aromatic, is linked to the enzyme via an ester linkage. The carboxyl group is linked to the serine hydroxyl as an ester. Okay, now we're halfway done. Now what we have to do is hydrolyze this ester. Okay, otherwise this wouldn't be an enzyme; it would be a reactant. What we do is now we have this big open space. Water is going to come in there to take the place. The water gets positioned here, and just basically the second part of this mechanism looks just like the first in many ways. Okay, except we're kind of reversing what we did in the first one. So now, So now if we draw the lone pair in here, which they didn't do, that will help to deprotonate the water to generate hydroxide, which attacks the carbonyl carbon. Now, the way they've drawn it here, the water attacks the carbonyl carbon as it gets and it gets deprotonated. Or so you could have water attacking first and getting deprotonated, the OH2 plus intermediate getting deprotonated. You could have histidine deprotonating water to generate hydroxide, which attacks, or probably close to the truth, both of these are happening simultaneously. That is, as water is attacking, it's getting deprotonated. And then these electrons go back to the oxygen. So the oxygen is acting as an electron sink. And once again, you're going to have a tetrahedral oxyanionic intermediate. So the carbon is tetrahedral now. What was the carbonyl carbon is now tetrahedral. And we have this unstable intermediate where this carbon's linked to 3 oxygens. One is the serine, one is this new OH, and one is the oxygen that's going to be the carbonyl again. But we're briefly stabilizing this. Now, the histidine moves back over to the serine, makes a new hydrogen bond with that serine, okay? Now, it is biasing the breakage when these electrons go back to occur here because the serine can take the proton. If it were to break here, if this histidine were still over here, it could donate a proton and just generate water and you go back. But if the histidine is now closer to the serine, it can protonate that. Okay. As these go back, you break the linkage between the carbonyl carbon and the oxygen of serine as it picks up a proton from histidine. And now you have a carboxylic acid. And now this guy can leave, and it will. And of course, this will immediately get deprotonated once it gets in the water. And we're now back to our serine hydrogen bonded to histidine, and we're ready to bind a new substrate. And that's the mechanism. And if we go back through it quickly, you'll see that the first half, okay, substrate comes in, attack by the serine, form a tetrahedral oxyanic intermediate, move the histidine over to donate a proton to the atom of the bond we're going to break. In this case, the nitrogen of the amide, which will be the nitrogen of the amine product. The second half looks much like the first. Now you exchange that C-terminal peptide for water. And now we're going to do exactly what we did before. Histidine acts as a base to abstract a proton as it attacks. Just like the serine attacked a minute ago, you form a tetrahedral oxyanic intermediate, and histidine moves over, donates a proton to the group that's going to leave, in this case, the serine oxygen. And we've now formed our product. So the two acts of this play are very similar to each other. They're kind of parallel, except in one case, we're acting on the serine oxygen, and in the other case, we're acting on the water oxygen. Okay. Now, this is a complicated model. Why do we have this model? Well, first of all, it explains a lot of data. These proteases in general can also catalyze ester hydrolysis. If you think about it, the second half is an ester hydrolysis, so that shouldn't be surprising. It's not very different breaking an ester than it is breaking an amide. So when it hydrolyzes esters, the first half of the reaction, the acylation reaction, linking the serine to the carboxylic acid of the ester, is very fast, okay, releasing the alcohol. The second half, the hydrolysis of that, is rate limiting, okay? So that means that as soon as you mix enzyme and substrate, you get one equivalent of one of the products very quickly. So for example, if we're using nitrophenyl acetate as our ester, so this is nitrophenol over here, that's one of the products. The other product will be acetic acid or acetate, okay? So what will happen very quickly is the serine will attack this carbonyl carbon, releasing nitrophenol, which has a much stronger color than the ester. It's actually yellow. And this is very, very pale yellow. This is bright yellow. Okay, so you can measure this in a spectrophotometer. And so you can mix the enzyme and substrate very quickly and immediately see one equivalent of paranitrophenol. That is, one equivalent compared to enzyme, because this reaction is slow. So when you're measuring the overall rate of hydrolysis of the enzyme, you're actually measuring this rate, the slow